Hi there. Thanks for joining us yet again. I don't know how you do it, but welcome along. This is Space Nuts with Andrew Dunkley, your host. Hope you're well. This episode is dedicated to volcanoes, supernovas that were not, and Voyager 2, which told us something that turned out not to probably be true. It's all coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us again to go over all of that is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. I'm still at large or on the loose really now, but that's all right.
Yeah. I've seen a few variations on what people think you should be called now. We'll keep an eye on those. If we get any good ones, I'll pass them along. You might want to change your business card. Yeah.
Yes, that's right.
Now, there's a story that we're going to start with today that brings into play something that I am very excited about, and that's volcanoes. I've visited several over my time traveling around the world, and you have visited a couple yourself, including that most infamous one that grounded all the planes in the Northern Hemisphere when it blew a gasket in 2010, was it?
2010, yeah.
The one in Iceland. What's it called again? Because I can't pronounce it.
Eyjafjallajökull. And it means, let me get it right. I think it means island, mountain, glacier. Jökull is a glacier. So the double L, there's two double L's in it, and double L is in Icelandic has the sound of t. It's not just a l, it's got a kind of squeeze of the cheeks before it. So it's Eyjafjallajökull. Eyjafjallajökull. On one of our visits to Iceland, a lovely guy who was our guide at the time, he said he'd spent a few years in Germany and I'd become fluent in German, so he spoke everybody in German. Came back to Iceland and got back into Icelandic, and he said his jaw ached because of what you've got to do to get the pronunciation out. And he said it wasn't used to it, his jaw started out.
Gosh,
I have to say, it's the only... Go on. That's right.
I was going to say, that explains why the Vikings were so angry all the time. No one could understand them.
Yes. Yeah, that's right. Anyway, it's good. I was going to say, that's the only Icelandic word that I know.
Yeah. And on our TikTok, you told us a very interesting factoid about it, which I think we should share again.
That it was the world's first carbon negative volcano because by grounding the world's airlines for something like a week, it was getting on for a week, it took more carbon out of the atmosphere than it put in, which is really quite an astonishing...
Yeah, it's unthinkable, isn't it? Because it was not a small eruption.
No, it's sending stuff up a long way, that's right.
And you've stood on the edge of that thing, haven't you?
On the edge of the glacier that runs over it, yes. So it's underneath the glacier, which is the Jökull bit of the word.
That's just too scary to think about.
I'll send you the picture. Actually, we might put it on the web. I've got a picture of me talking to the ABC right at the snout of the glacier that runs over Eyjafjallajökull.
Well, one volcano that we visited ended up erupting not long after we were there, as is our habit. Whenever we travel, something happens. And it stopped air traffic around the Asia-Pacific region for a while. That was Mount Yata on Vanuatu. And as we speak, one airline that I'm aware of has cancelled all flights out of Denpasar in Indonesia, Bali, because of another volcanic eruption.
Yes, eruption there. Yeah, it's all happening.
It is certainly happening. Now, that's our planet and its active volcanoes, and we know of a couple of other places in our solar system that seem to have volcanic activity, maybe Venus. Io, was Io one of them?
Yes, indeed. It's probably the most volcanically active body in the solar system is Io.
Yes. But we are talking about an exoplanet that they think might be volcanic. That's quite a find.
It is. It rejoices in the name. Let's get this out of the way. L98-59D. And that planet was a discovery from the TESS Space Telescope, which we've talked about a lot because it was the space telescope that really followed on from Kepler, which was a telescope designed to look for the dip in the light of a star because of the planet going around it. Likewise, TESS did the same thing, and both those two together absolutely revolutionized the science of planet discovery. So L9859D, discovered by TESS back in 2019, and has now been analyzed in some detail because of the technology that we can apply. I've got a feeling this has come from the JWST, but I need to check that. Anyway, yes, that's right. It has been James Webb Telescope observations that have given us this new information, which is that that particular planet, L9859D, I do like the name, has signatures in its atmosphere of some of the products which we know are associated with volcanic eruptions. And so sulfur dioxide is one of them, and hydrogen sulfide, bad egg gas, that's another.
Ugh.
And what the scientists who've done this work are suggesting is that the presence of those, combined with the absence of other ones, which are much more common, like carbon dioxide, the presence of those suggest that we have extreme conditions on L9859D, either volcanic activity on a big scale, or even a molten surface. Now, we think that at some stage in its past, the Earth's surface was molten. It was what we call a lava world. And we may be seeing this particular planet basically doing the same sort of thing. So just to give it some statistics, Andrew, it's about 50% bigger than the Earth. It's what we call a super Earth in the scale of exoplanets. It's about 35 light years away as the crow flies. And it has a record. It's a record breaker because if the details of these observations are confirmed, and they're still fairly tentative, the details of the chemistry of the atmosphere, if they're confirmed, I beg your pardon, it will be the smallest known exoplanet with an atmosphere. So it's interesting because we're now starting to probe down to Earth-sized planets here with the ability to use spectroscopy to determine what's in their atmospheres. So a really interesting observation, yeah.
Absolutely. And it's not that far away, this one, is it? Either, is it?
35 light years. No, that's right. It's, it's certainly within the sun's local neighborhood. So not that makes it any difference. It's once you get beyond the orbit of Neptune, you're talking about a different sort of distance scale altogether from what we're used to in the solar system. But nevertheless, it's good. And just a quick footnote to how we can measure what's in the atmosphere of an exoplanet. And that it's a very, very delicate measurement and needs the best instrumentation. What you do is you wait until the planet transits in front of its parent star, and you look at the spectrum of the parent star, and then you compare that with what the parent star looks like without the planet in front of it. Because the difference in them is caused by the light of the star passing through the additional layer of the atmosphere of the planet, which is sitting in front of it. And so even though that atmosphere might be very small in diameter compared with the diameter of the star, in fact, it's a ring, of course, because you've got the planet itself blocking it, that area is very small compared with the surface area of the star as we see it. It's still, with the sensitive equipment that we have now, it's still possible to tease out what the spectrum lines, the spectral signature of the gases in the atmosphere of the exoplanets are. And it's a technique that's being used more and more, and I think has a great future. And of course, once we get into the ELT League, the Extremely Large Telescope League, this will be a standard kind of measurement that we'll be hearing about every week, I'm sure.
Yes, that's very exciting. I remember going to a lecture, I might have emceed it once, where they were talking about using spectrographs, I'll say, to analyze exoplanets. And now it's sort of becoming the norm, which is very exciting. That forecast was spot on.
That might even have been one of the
Bach lectures.
No, was it the Bach lectures? That's right.
Yeah.
That, I was involved in. Yes, the Bach lectures.
Yeah. Now, I did have a question. Do we think that L98-59d is independently volcanic, or is it being influenced by something else? EO is kind of volcanic because Jupiter gives it a bit of a crushing hug all the time.
Yes, exactly. That's right. And that's a great question. And the answer is probably, because it goes round its parent star in, if I remember rightly, it's just a few days. I can't remember just exactly how many days it is. You might have it in front of you. Yeah, 7.5 Earth days. So what we take a year to do around the sun, that particular planet takes 7.5 days to do around its parent star. So it means it's very close to its parent star, and much closer than Mercury is to the sun. And that's another reason why it might be volcanically active to the degree that we think it is. And it's not just the radiant heat of the star itself, because it's close by. It's that closeness that gives the planet a squash and a squeeze every time it goes around, and causes this heating of its interior by what we call tidal forces. Exactly the same mechanism that keeps Io volcanically active.
Yes, so it's a bit bigger than Earth at 1.5 times our size, but it's surprisingly much stinkier place.
We talked about H2S in a recent episode, didn't we? Because it was the nickname given to the radar that was used on Lancaster bombers.
That's
right. That was the nickname,
right.
The H2S, yeah, because it smells bad. That's what they said.
Yes, absolutely. And if you want to read about that particular story, phys.org, of course, phys.org. Just do a search for A Distant Planet Seems to Have a Sulfur-Rich Atmosphere, hinting at alien volcanoes. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Now, Fred, we get questions semi-regularly about supernovae, those cataclysmic explosions of stars that can be, sometimes seen in daylight if they're close enough to us, and there's been a couple in recorded history, and they ultimately collapse and become a black hole. Now we've got a situation that's so unusual and somewhat rare, a supernova that did not happen, but the star still turned into a black hole. That is sort of on the realm of weird.
It's weird, that's right. Although sort of understood, the mechanism is, predicted by theory that you can do this. But it is so unusual. We always think of black holes being formed in supernova explosions. And here we've got something that doesn't detonate. So it basically, the collapse takes place without the explosion. And just to recap why stars do collapse at the end of their lives, you have a situation during the normal lifetime of a star, and our sun's in this situation, where the outward pressure of the radiation coming from the nuclear fusion in its center, and that's what makes the sun shine, that has a pressure on the gas of the sun, and that just balances the gravitational pull of the whole thing, its own self-gravity. And so you've got this balancing act between the radiation pressure and the gravity. When the sun or the star runs out of its fuel, hydrogen fuel, that changes. So the radiation, it actually goes through a few complex phases, but eventually the radiation stops. And so the battle is won by gravity. Gravity tries to collapse the star into, well, if it can, a black hole, but it needs to be more than about 8 times the mass of the sun before it will do that, perhaps even 10 times the mass of the sun. So that's the process, and it's that sort of collapse that takes place. What you've got is heavy atoms basically mixing with light atoms and transferring their energy to them. I used to do a trick with ping pong balls that demonstrates this quite nicely. That if you have atoms of different masses in close proximity, some of them fall and some of them don't. Some of them bounce outwards, and that's what gives rise to the explosion. But with what we've seen in this, it's actually in the Andromeda Galaxy, the star itself. It's basically a star that's been studied for a while and has now just disappeared. And it was known to be a star of the sort of mass that you would form a supernova, but it's just gone, and so we believe that has created a black hole without the explosion. This research is being done, led actually from MIT, Massachusetts Institute of Technology, the Kavli Institute for Astrophysics and Space Research. So it's, as I said, it's in the Andromeda Galaxy. It's been observed over a number of years. It did actually brighten for a while, and this is in the infrared wave band back in 2014. I should give it a name since we like giving stars names. It's called M31-2014-DS1. And it brightened in 2014, but then it stayed bright for about 3 years, but then for another 3 years it faded away and has now disappeared. And in 2023 it couldn't be detected in imaging observations, so it's gone. It's thought to have a mass of about 6.7 times the mass of the Sun, and basically has essentially vanished as a black hole without what we call an optical outburst, in other words, without a supernova explosion. So it's kind of like a dud. It reminds me of when you lit fireworks and they didn't go off in the days when you could do that yourself.
Yeah, it is a very odd one, and I suppose it's because it wasn't quite big enough. Would that be the basic reason for it not doing what a supernova normally does?
Yes, I think that's right, although it's a very complex process. And once again, we have a very nice article about this on phys.org, which also references the paper, which is currently, I think, being peer-reviewed. It's the paper's title is The Disappearance of a Massive Star Marking the Birth of a Black Hole in M31. M31 is the posh name for the Andromeda Galaxy, Messier 31. But it's a process that has nuances, and the reason why I mentioned the phys.org article is that it describes those nuances very well, and there's a whole section which starts with the sentence "Supernovae are complex events." Then you can read on, and you'll see what's happening with the burst of neutrinos, the neutrino shock. All of these things, are part and parcel of what makes a supernova. And sometimes there's this what's called the neutrino shock, which apparently also always stalls, but usually revives again. And that's what causes the supernova to explode. The neutrino shock was not revived, it says. So let me read a little bit from the article. Which says, in M31 2014 DS1, the neutrino shock was not revived. The researchers were able to constrain the amount of material ejected by the star, and it was far below what a supernova would eject. And there's a quote from one of the authors, from the paper actually. These constraints imply that the majority of stellar material, that's more than 5 times the mass of the Sun, collapsed into the core, exceeding the maximum mass of a neutron star and forming a black hole. About 98% of the star's mass collapsed and created a black hole with about 6.5 times the mass of the Sun. So it's one of these things where we really struggle to, those of us who aren't absolutely immersed in the physics struggle to understand the details. There's a lovely sentence, which I like very much in the Viz.org article. M31 2014 DS1 isn't the only failed supernova or candidate failed supernova that astronomers have found. They're difficult to spot because they're characterized by what doesn't happen rather than what does. A supernova is hard to miss because it's so bright and appears in the sky suddenly. And ancient astronomers recorded several of them, but there are other ones that have been found that have just disappeared, as this one has.
Yeah. So usually when a star explodes supernova style, it produces all these really incredible elements that are well documented. This one, I assume, would not have done that, so it didn't pay its toll.
Maybe not. I'm not well enough versed in supernova physics to know the answer to that definitively, but I think you're probably right, Andrew, that it didn't, dish out gold and platinum and all the other stuff that permeates the universe from supernova explosions. I think that will be the case, that the ejected material is much too small for it to have paid its toll, as you've said.
Yeah, so no lithium, no blue tack. Gee.
None of that stuff.
Yeah. What are we going to do? Okay, that is a great story, and something a little bit different. And I'm guessing we'll get some more black hole questions about that. So, does this? Well, I'll ask one because someone's probably wondering: will this be a different kind of black hole? Will it be unusual in some respects because it wasn't birthed by a supernova?
I don't think so. Black holes are characterized by very few parameters. Like one of them is the magnetic field, one's the spin. And so there's not that much to differentiate between one black hole and another, except for the mass. And the mass is not that much different. It might be a bit smaller than what you would get from a bigger supernova explosion. There's a theorem that I always like the name of about black holes, and it's called the no-hair theorem. And you can understand why I quite like that one. And the no-hair theorem basically tells you that you can't see very much from the outside of a black hole. So, no hair just doesn't give you much of a clue about what colour somebody's hair might have been. I'm not quite sure where the term comes from, but the no-hair theorem is one that tells you that there's very few parameters that you can measure outside a black hole. So they're all much of a muchness, except in their mass.
Okay, interesting. All right, there it is. It is another story on phys.org, PHYS, as I keep reminding you. And fascinating and unusual event. This is Space Nuts, Andrew Dunkley and Professor Fred Watson here.
0G, and I feel fine.
Space Nuts.
To our final story, Fred, we're going to look at Uranus. No, we're not. We don't want to do that, but we are going to look at the planet. And, sorry, couldn't help it. Any opportunity. This is really interesting, though, because when Voyager 2, which is the only spacecraft that's visited Uranus, as far as I'm aware, went by, took measurements and sent the data back, and we all went, oh my gosh, this is unusual. How interesting. Wow. Now they've revisited the data and gone, oh, hang on a minute. If it had arrived, I love this bit, 2 days earlier, the readings would have been completely different. This is a really fascinating story.
I think so too. And it's, we've always thought Uranus was a bit peculiar. It is peculiar because it's lying on its side. It rotates with its north pole just below the plane of its orbit, which means it's tipped over by about 98, I think, degrees. And that probably is the result of a collision at some time in its past history. But it's also had other aspects that have puzzled astronomers. Very, very odd magnetosphere. So the magnetosphere is the region around a planet which is dominated by its own magnetism. And the magnetosphere has been thought to be highly asymmetric, very unusual in shape, and to have strange, the phenomena to do with the moons of Uranus have thought to be been unusual. That there was no evidence, for example, of there being any kind of ice, the conventional ice moon idea. The reason for that is that you detect the sub-ice ocean of a moon by its magnetism, by sensing it with a magnetometer. And if you can't detect it, then you suspect there isn't any ocean. Whereas in the case of Uranus, it now is thought that because the magnetic bubble that the planet lives in was highly distorted, maybe that interpretation was wrong. And as you said, if it had arrived 2 days earlier, we would probably have had a better idea of what was going on. And the reason why that 2 days is important is because of a solar flare, an emission of plasma from the sun that reached Uranus kind of just before Voyager 2 got there, and totally distorted the magnetic bubble in which the planet lives. So really, very, very, an unusual and perhaps misleading set of observations or deductions were made from the Voyager 2 data, which, with hindsight, might be incorrect. And that hindsight is coming about because people are reanalyzing the data of Voyager 2. It's something that I think is great, that we constantly look back at what we might call old data, old information, and you can learn new things from it. And there's a comment by one of the great planetary scientists of the present day, who works at JPL and is somebody that we know, Linda Spilker. She was the project scientist for the Cassini space mission. But back in the day, she was also among the Voyager 2 mission scientists when the flyby took place in 1986, the flyby of Uranus. And there's a nice quote from her, again, in one of the articles that we've been looking at. She says, the flyby was packed with surprises, and we were searching for an explanation of its unusual behavior. The magnetosphere Voyager 2 measured was only a snapshot in time, and this new work explains some of the apparent contradictions, and it will change our view of Uranus once again. So she's commenting on this new research. A veteran observer, a very interesting person who was a delight to host back in whatever year it was, might be 2017, I think. I think it was 2017, just after the end of the mission, this Cassini mission. She gave our Alison Levick lecture here in Sydney, so that's how we got to know her.
Yes, of course, behind closed doors, everyone's going back to the original team that oversaw Voyager 2 and said, you had one job.
Yeah, maybe that's right. On the other hand, research is like that. Sometimes you bark up the wrong tree for decades, as we've seen here.
What it's proven, though, is that Uranus is ordinary.
It's more ordinary than we thought it was. That's right.
Yeah, more ordinary than we thought it was. It's like the other gas giants in that respect, but in other ways it is quite unusual and unique.
Yeah.
Indeed. Yeah. There's a great article on that at cosmosmagazine.com if you want to check it out. That's where we're going to end things. Fred, thank you very much.
Thank you, Andrew. It's been a delight to talk, as always.
Yes, I like talking to you. My wife won't talk to me, but talk to you. I don't know what's going on there. But anyway, we will see you next time. Fred, thank you very much.
I hope so, yeah.
Fred Watson, astronomer at large. And Hugh in the studio. What was Hugh up to today? Nothing. Didn't help us, didn't help his wife, didn't pick up the kids from school, didn't do anything. That's Hugh. Although I must say, we're getting a lot of emails from people saying, can't you be nice to Hugh? No. And from me, Andrew Dunkley, thanks for your company. See you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.